So Paul is at Northeastern now. He used to be at Rice. He joined us last year, and we're very fortunate to hire him away. He's a very strong applied mathematician, and he'll be telling us about deep decoder.
Well, thank you, Ravi. So as we know from the past decade, neural networks are very good at generating natural images or natural-looking images, along with solving image recovery problems and inverse problems and other tasks involving analyzing images. So what this means is that somehow these networks understand what it means for a particular collection of pixels to be natural. Now, certainly, a lot of the learning aspect of neural networks is going to help explain why they know what looks natural, but it's widely believed that architectural concerns also hand you some aspect of naturalness of images. Right? So now, unfortunately, networks that are out there in the wild are often so complicated and have so many parameters that it's hard to identify exactly what about them makes them well-tuned to process natural images. So what this work is about is to introduce a new neural network called the deep decoder, which is a particularly simple network, which has very few parameters and can act as a natural signal prior. Right? So before we give a brief overview of like what it means to have like a model of natural images, let's set the stage a bit. Right? So let's remember, right, if you're recovering images from little data, then it requires that you have a model for images. And this is just a fundamental mathematical fact, that if I have, say, a 3000 by 2000 pixel image and 256 values of color and 3 channels, I have a lot of bits. But if I do some sort of compression or some intelligent representation, then I can get away, say, for example, with 500 times fewer bits in this example. And so this all comes down to what is the way of modeling natural images. Now, there's a common way, perhaps one of the most common ways right now, is through viewing them as being sparse with respect to a particular basis. For example, say a wavelet-like basis. And so you could have basis elements that look something like this, and then you could take any image and you could expand it against these images, and then it turns out that you end up having natural images be sparse with respect to this representation. Right? So what's nice about this perspective is that it doesn't require any training data. Right? In fact, this perspective sort of precedes sort of like the deep learning movement. So no training data is required here, which is also to say there is no learning. However, the drawback of this model is that it is a linear signal model, which is to say it assumes that a signal is in the linear span of a few elements in this space. And that may not be the best representation. So one could look at this and say, I want to improve on this. I could say, why should I handcraft these particular basis elements? Why don't I learn them from data? And so then that leads to like a sparse coding or dictionary learning perspective, where say you might learn from data a bunch of individual images that you can then combine in order to recover your particular image of interest. And so then when you do this, you may get like particular images that look something like these, which happen to have a lot of visual overlap with, say, wavelets. So here, this is a case where you have training data and you use it, but fundamentally, this is also still a linear signal model. Right? So now, with the advent of deep learning, then there are neural network-based models for natural images, which come a couple of varieties. So, for example, one can have an autoencoder, which could take, say, some input image and then output an image that's meant to be the same or meant to be very, very similar. And then this allows you to do things like train networks in, let's say, like an end-to-end fashion to do image processing tasks. And then other neural nets can be built, for example, these generative adversarial nets, which can generate natural images based on low-dimensional latent representations. Right? So the perspective here is that, yes, we have a lot of training data that is needed in order to train these models. However, they are nonlinear signal models, and hence they can perhaps better capture the dynamics of what natural images really are. Right? So, and like these tools are very useful in practice, and there are entire companies built on them. And so here's a company which can, for example, compress your images using artificial intelligence. Right? So this talk is about a different paradigm of modeling natural images. And in particular, it's about using untrained neural nets as image models. Right? So what this means is that there's going to be some neural network, but it is going to be untrained. And by untrained, I mean there is no training data. Right? There is no training phase. There is no loss that is being optimized over some training set. What this then in practice means is that, say, there is some input to this network, which, say, you could take to be random, and then the network originally has random coefficients all throughout. And then what you want to do is somehow map that random noise through a bunch of weights to, say, this particular image. Right? So this is very similar to, say, like the wavelet perspective of representation. Right? There is one image, and with a wavelet point of view, you're going to say, how do I write my image with respect to this representation? Like, which wavelets do I have to add up in which amounts in order to get my image? Right? So in wavelets, there is no learning. Right? So in the same sense here, there is no learning. You're handing it one image, and you're handing it one random vector in, and then a neural network is going to map that random vector to this particular image. So this has the characters of this wavelet perspective, which is to say, in some sense, it's handcrafted. And the handcrafting is about the architectural details of this network. Right? So a human comes in and says, I want this architecture in order to map this particular bit of noise to this image. Right? So it is not learning from data. So the other perspective is that this is also a nonlinear signal model. So it's capturing a lot of the benefits of neural networks. Right? So now the conclusions, the takeaway message from this talk is that we're introducing a new network called the deep decoder. And this is a particularly simple network that is very effective at representing natural images. So it's untrained, meaning all you have to do is hand it one image. It knows nothing about other images. It knows nothing about semantics. And what it can do is it can yield image compression on par with wavelet compression. And so then the reason that it can do this is because it's an under-parameterized net, which is to say it has very, very few weight parameters. So now this is very different than, say, like an autoencoder, which may have a bottleneck phase, and in that bottleneck phase you have very few parameters. But overall, in an autoencoder, you may have a lot of parameters. Here, there are very few parameters, period. Right? And so then the reason it has so few parameters is because it's simple, and then a benefit of being simple is then it affords some theoretical guarantees, which is why I thought it would be great for this venue. Right? All right, so let's talk about what is the deep decoder doing. So I'm not going to tell you the architecture of it just yet, but I want to set it up for how do you represent an image using a deep decoder. And for now, a deep decoder is really just some function. Right? So the deep decoder, it's a non-learned image model where a high-dimensional image is going to be represented as the output of a neural network, which we'll call DD, of a bunch of coefficients. Right? So you should think of these coefficients as the weights of the matrix, of the network. Right? So don't think of these coefficients as the input of the network, because that input is going to be fixed. But here, think of it as, to specify the network, I have to specify all of the weights, and I'm going to tuck those into this low-dimensional coefficient vector C. Right? And so now, how do I represent an image? Where I'm going to say, you hand me an image, and then I'm just going to find the coefficients, the weights of my matrix, or of my network, that then best represent that image, let's say in an L2 sense. Right? So this is a relatively straightforward formulation. It's exactly what you would think of say from a wavelet representation or other sorts of representations, right? And so just to cut to the chase here, right? So with the architecture that I'll tell you about in another slide or two, then we can say take this image on the left, we fit this one network to that image and say we can get a compression factor of 30.8 for this image. Right. Now, to put that in context, let's compare this to wavelet thresholding. So here, what's being plotted is a comparison when you take the same image and you're going to allow yourself a certain compression factor, so 30 on the left and say 7 on the right. And then we're going to look at what's the peak signal to noise ratio under the deep decoder and under wavelet thresholding with exactly that number of parameters. So then the red line is where it's equal. So any point above the red line is to say that the deep decoder is doing better than wavelet thresholding at representing this natural image. And so what we see with this architecture is that, so here's like a whole bunch of images from ImageNet, and at very high levels of compression, then the deep decoder does better than wavelet thresholding. Now at relatively low levels of compression, wavelet thresholding will do better, and this is expected because as you have more and more measurements, like the wavelets will allow you to represent your signal exactly. After all, let's say it can be a basis, and so like it's expected that that will happen. But of course, what's really interesting is the the high compression regime, right? So what this is really showing is that this network is a very effective, is a very concise image prior. So the number of parameters that it needs to completely specify this image is very small. Right? So now, okay, so what is this network? I've been promising that it's simple, and this network like looks as follows. So there's going to be some input, which say we'll call B1, and let's say there's like N1 pixels and K1 channels. And then you're going to have a sequence of layers, which is just the same thing repeated over and over again, where at each layer you have just point-wise linear combinations of the pixels. So that's given by this C. So then after that, you're going to upsample your image through just linear upsampling, and that's that U, and then you'll hit it through a nonlinear activation function like RailU. All right, so all that happens here is you do pixel-wise linear combinations, you upsample, and you take a RailU. And so then here you can go from some low-dimensional like input to this high-dimensional image using this. And then at the last layer, let's say you want to output your particular image, so you have to learn, or you have to estimate one particular convolution, or excuse me, one particular point-wise linear combination. Right, so here, the point here is that the input to this network is, let's say, random and fixed, and it's the weights of this network, these C's, that have to be estimated to fit the one data point exactly. Yeah. So here again, the parameters are just these weights C. All right, so let's contrast to this, like what does like a real neural network like look like out in the wild? And let's say I have a UNet architecture for, say, an autoencoder, and it might look something like this. And my point here is that we're very used to having very complicated architectures, which one could argue have not really been optimized for simplicity, perhaps because they didn't need to be. Right? And so here, like in this architecture, you have all these convolutions, sometimes 3x3 convolutions, you have your max pooling, you have upsampling, you have more convolutions. And so it's very difficult to, well, and in addition, you have these skip connections. And so it's very difficult to understand which part of this network is really encoding what is natural about natural images. Right? And if we want to look at, say, one aspect of natural images is that neighboring pixels are related in particular ways. I mean, there may be discontinuities, but maybe it's piecewise smooth in general, but that is somehow baked into what a natural image is. So if I look at this architecture and say, which bits of it are responsible for coupling the pixels together in an image, and I see almost everything, right? I see the up convolutions do it, the convolutions do it, the max pooling does it, the IP connections draw it. So there's really, this network is so complicated, it's hard to understand what aspect of it makes it good for natural images, right? So now that we've introduced the deep decoder, like what can we do with it, right? Well, we can solve inverse problems. And this can be done in a fairly general way. And so how would this work? Right? So with an inverse problem, like I have some forward model, which I'll call F, and then you have some F of some image, and then maybe there's some noise added to it. And so given F of some image plus noise, your goal is to recover the image. Right? So let's look at this, like in our framework. So if the image is the deep decoder of a coefficient vector C, which again was all the weights of the matrix, then the recovery process was optimize the L2 norm of your measurements minus the forward model of the deep decoder of the weights C. And then just choose the best C to fit these measurements. Okay? And now, once you have that C, then just run it through the deep decoder with your fixed input that was set in advance, and then now you've recovered your image. So we can look at this, say, in the case of denoising, which is an interesting starting point, both because it's very relatively mathematically simple, but also it's of very high practical importance. And then there's comments that inverse problems can be sort of solved by having denoising steps at every chain of an iteration. And so this is an important fundamental task to start with. So here's some empirical results comparing deep decoder to other methods. So like here's an image on the left, and then say there's some noise added to this image. And so then what this is showing you is the recovery from the deep decoder given only the noisy image. Right? So after all, it's given only one image, and it's given the noisy image. It knows nothing about what's going on in the image. It knows nothing that there is noise in it. All it does is it tries to represent that image exactly, but it can't. What it does is it automatically denoises the image. And so then there's these other methods, for example, something called the deep image prior, which I'll talk about in a few slides, which the deep decoder does a little bit better than in this example. And then there's other non-learning based methods for denoising, for example, BM3D, which is considered the state of the art for non-learning based methods. And so here, this is very promising performance because this architecture out of the box is behaving as well as this BM3D method, which was a field of work for decades of effort, ultimately culminating into BM3D. Right? So then you can solve other problems with it as well. Like, for example, you can solve in-painting problems with it, and it has performance on par with other methods that are out there. Right? So this comes to a question like, why does the deep decoder work? And at some point, it's all about what does it mean to represent images. Right? So with many parameters, the deep decoder could represent any image. Right, so if I had a system which had a ton of parameters, like more than the number of pixels in my image, then this sort of architecture would be able to fit any image exactly. But that's not what we do with it. What we actually do is we consider this deep decoder with very few parameters. And so the point here is that the reason the deep decoder works is because it approximates natural images well, but it cannot approximate noise well. And the reason for this is because it doesn't have that many parameters. So once we now have a parameter budget, we cannot fit anything. Or rather, we cannot fit everything. Right? So let's look at some empirical performance here. So let's say like you take an image, you have a noisy image, and you're going to solve for the deep decoder with this image, which is to say you're going to find the best weights to represent that image. And so what happens is exactly what you would expect to happen. Like initially you have a lot of error, and then as you continue this solving this optimization problem, your error is going to decrease, and then the error actually levels out. And that's important because that is at some point, there's a noise level to the image. If you didn't level out, you wouldn't denoise the image. So now, if instead you hand the deep decoder a pure image with it's not noisy, then what you get is, again, you start a high error, and then you end up decaying to basically to zero error. Not exactly zero, but to much less error than, say, for the noisy image. And so what this is saying is that the deep decoder architecture can fit natural images. So what happens if you hand the deep decoder pure noise? Well, then let's say you start off with a bad representation and you learn a little bit about that noise, but then more or less you plateau right away. Right? So this is really convincingly showing like the deep decoder cannot fit noise because it doesn't have enough parameters. Right?
Just make sure I understand. So when you get a noisy image, you take your deep decoder and then you give it some arbitrary noise and try to get it to match this noisy image. And then afterwards, you feed that noisy image through and it denoises it. Is that how they...
Yeah, so like you have, where is... So like here, like you hand it this image, what you try to do is you hand it your noisy image, right? Then fixed in advance is some fixed random input, which you can consider that arbitrarily chosen and fixed. And so then what you do is you run an optimization problem to try to fit that noisy image that you get. But you'll never actually get the noisy image because there isn't the representational capacity in the network to give it to you because the network is underparameterized. Yes? So yeah, in the architecture here, so the main ingredient is the pixel-wise linear combinations, which you could interpret as a one-by-one convolution if you wanted to, right? So, but the reason that we phrase it as point-wise linear combinations is because, like, a convolution leads you to think that it's really coupling the pixels together, whereas really what this is doing is not that. It's just every pixel at that step is on its own. The only thing that couples pixels together is this upsampling. So what we've done is in this architecture, we've isolated the part that actually relates pixels to each other as only being given by an object that doesn't need to be learned, right? It's just straight up upsampling of your image. Right? So now you do have to estimate some things from your image, and that's, exactly what all of these linear combinations should be. All right. So here again, the point was that because you have very few parameters, you cannot fit noise. And if you can't fit noise and I hand you a noisy image, then you're going to fit the good part of the image, but you can't fit the bad part of the image, and that's why it is an automatic denoiser. Right? And so now you could say, well, but can you fit the good part of the image? And here's just an example, like in one dimension, let's say you handed a piecewise smooth function. So say here you have this smooth part and you have these jumps. And so we trained a one-dimensional deep decoder and it likes it, right? It can represent it quite well. Yep. So this being a theory venue, I want to talk about like the theory opportunities that this affords. Right, so one thing that's very interesting about this model is because it's so simple, it actually affords theory that normal convolutional nets that are really complicated might just be too difficult to acquire. And so this theory is about like how well can it fit noise? Or rather, it's a proof that it cannot fit noise very well. So let's set the stage. Right? So here, let's say we have a one-layer deep decoder, and it has m parameters. Right? So that's like the number of coefficients in all those pixel-wise linear combinations. And so let's say the output dimension has dimensionality n, and then let's say z is the standard Gaussian noise. So that is to say you're trying to fit a purely noisy image, and we're calling that image z. Right? So the claim is that with high probability, the best that a deep decoder can do at representing z is pretty bad. It's the norm of z, or like the minimum deviation from it is 1 minus something like m over n times the norm squared of z. So which is to say you can only fit m over n of that noise. Right? And so if the number of parameters is less than the ambient dimensionality, that means that you can only fit so much of that noise power. Right? And so here, right, so typically for this deep decoder, we would choose m to be much less than n, and so then this deep decoder like provably filters out noise. Right? Now, like this result really makes sense. Let's consider just like in the case of like a subspace. Like suppose you're in Rn and you have a subspace of dimensionality m, and I take a random noisy vector and I project onto this space. Like how much noise do I reduce by? Well, it's by m over n. Right? So if m is very small, then I have quite a bit of noise reduction. Right? And so then the same thing that we have in our theoretical result is that the noise energy is reduced to a fraction of m over n, but of course there's some other factors that come up that depend on the network architecture, such as D, which is the depth of the network, and log n, log of the number of the output dimensionality. Right? So this is up to this D and logarithmic factor is exactly what you would expect. Right? So just to give you like a sense of like how does this proof work, right? So this would say like we're trying to find a C such that G of C fits some particular point, and so let's just say that let's look at the range of G. Right? G is going to be given by say the ReLU of the upsample version of some input matrix B times this linear combination matrix C, and then with the last layer of the deep decoder also did another linear combination just to hand you a single, say, channel output image, right? So in order to analyze this, we can view that ReLU as an object which either like keeps you +1 or 0 based on whether the ReLU is active or not. And so then you can write G as actually being the product of this matrix with this vector where we take this matrix here, and then it's either multiplied by some matrix which is diagonal and is, say, 1 where the ReLUs are active and 0s where the ReLUs are non-active. So now I can say everything in the output of G is of this form, and so then this is saying that there are there's a k-squared dimensional subspace for each one of these realizations of like the activation patterns. And so then the question is, how many subspaces are there? Basically, if we can quantify the number of subspaces in which the output of this lives, then we can talk about a denoising result. Right? So how many subspaces are there? Well, that goes to basically how many different patterns of activation can you get from the ReLUs? And then this comes from a basic sphere covering result. And it turns out that, say, like if you hand me, say, some matrix in n by k, and then I go, well, what are all of the different sign patterns I can get by hitting a ReLU on A times an arbitrary vector? Well, that ends up being n to the k. And so here there are sort of like k columns. And so then if there's n to the k choices, then there's n to the a piece, then there's n to the k squared total choices. So what this means is that the output of this deep decoder lies in the union of n to the k squared many k squared dimensional subspaces. So at this point now, a straightforward union bound will hand you the worst case performance you could get. Right? So this is just meant to show you the tools that are involved. There's a lot of counting arguments about sign patterns, and this is something that's going to come up over and over again in any theory about deep learning literature, because those sign patterns are not arbitrary, right? They're very confined in their number. Right? Okay, so now I want to change gears a little bit and talk about like another method that's out there that's somewhat similar to the deep decoder, and it's something which I mentioned before, and it's called the deep image prior. Right? So the deep image prior also lives in the same framework for image representation, which is to say it's a neural network that is not learned, that is meant to fit a particular image. Right? And so here the key difference with the deep image prior and the deep decoder is that the coefficients of this network are high dimensional. And this is because of the architecture of that network is very, very complicated and has very many parameters, and in particular has convolutions. And even like a 3x3 convolution is going to hand you 9 parameters per channel, which is going to add up very, very quickly. Right? So once you have this, the best representation is computed in the same way, which is to say you have an image, and the deep image prior is something like an autoencoder. And so it's going to basically try to run your image through this autoencoder, and then it's going to optimize the weights of that autoencoder to try to fit exactly that image. And now the concern is that because there are a lot of parameters here, and that network can fit anything, you actually have to stop this optimization early. Because if you don't, the large number of parameters will allow it to fit an arbitrary image. Right? So here we can see this in like the empirical performance at the denoising task. Right? And this is really meant to emphasize the point of the number of parameters that you have in your neural network model really matters. Right? So here what we're doing is we're comparing the deep image prior and the deep decoder, let's say for representing a noisy image. And so what we saw with the deep decoder is what we saw before, which is representation goes down as the number of steps of your optimization increases, and then it levels out at some non-zero level, which is to say it's not fitting the noise. So what happens with the deep image prior is that it starts at a high representation error, and then that goes lower, but then it begins a separate phase where it starts overfitting to the image. And so this is something that we see over and over again in this literature. If you can run some of these networks out toward infinity, you might actually get worse performance. And so here what's happening is that the network then starts learning the exact noise pattern of the image, meaning that it is not denoising the image unless you cut it right there. So then what the deep image prior requires is for you to regularize it with an early stopping in order to have a hope for it to do denoising. So then in both cases, like if you hand it like a natural image, both of these models actually can represent that image more or less exactly. And that's because if your image is natural and you fit it exactly, that's fine. That's sort of the goal. Right? But if it was unnatural and noisy, then you wouldn't want to fit it. And then there's a similar behavior in the noisy setting where the deep image prior eventually starts fitting to a lot more of the noise. Right, so here, again, the point is all about the number of parameters here. Like we're so used to having networks with a very large number of parameters that if we have that large number of parameters and we can fit any image, then that means that the model itself is not actually hitting at what it means to be natural. So in order to have a hope for the model to represent what truly is natural, then we can't have this over-parameterization. So this is to lead to sort of a mathematical puzzle, which I'll just propose, and I won't analyze anymore like during this talk, which is like, what is this deep decoder doing? Right, so it's something which is given a bunch of random input vectors that are fixed, and then it's saying, I need you to transform these input vectors into this particular image of a heart or whatever. So now that's a mathematical challenge. All your only tools I'll allow you to have are linear combinations, linear upsampling, and RailU. So now, how do you take the noise and induce structure and pattern in that noise to then fit this particular image? Right? That is what is going on. Right? So in summary, what we have here is so the deep decoder is this new neural network architecture, which is meant to be a natural image prior. Right? So it's meant to be a model for what makes some particular images natural and other particular images unnatural. Right? So it's particularly efficient because it's under-parameterized, right? Which is to say the number of coefficients that it has is very few, and if you tune that well, then you can represent natural images quite well. And the important thing is that it uses no training data. And so in cases where you don't have a lot of training data or where training data is very expensive to acquire or unethical to acquire or like not legal to acquire, then this may be a tool that could be very useful, right? So it yielded compression and image restoration on performance of the state of the art. And a central aspect of it was, again, the simplicity, which then allowed for theoretical guarantees which we're not accustomed to about other architectures. And so with that, I'll thank you for your attention.
Yeah, so what happens if you learn the parameters and then change the input to the network, the random input that you are keeping fixed? Do you get other natural looking images or do you get garbage? Or?
Yeah, so if you train a deep decoder and then you change the input vector, then you're going to more or less get garbage, but it's not totally random garbage. What it's going to be kind of like noise that's been blurred a little bit. And so this is because the architectures learn how to take noise and turn it into some shapes. But if you hand it different noise, it's not going to really look natural. It's just going to be kind of blobby, but not totally random.
So you emphasized on underparameterization, right, as the key for denoising, but for optimization, there's a lot of arguments that overparameterization helps a lot, and it's hard to optimize underparameterized models. So what's been the experience here?
I think, well, I guess the experiments show that the optimization works once you're in the right parameter regime. And so I don't have any thorough comment to say about whether it works better in the over-parameterized or under-parameterized case, because if you're in the over-parameterized case, the whole method fails, because then you're going to be able to fit to the noise. So it's a little bit like, even if it is easier to optimize in the over-parameterized case, that's not what you want to do. However, we don't have problems fitting these images in the under-parameterized case. And I mean, on Reinhard's GitHub, there's like a Python notebook which you can download, and the representation of these networks is quite reliable. Which is to say, like, the same hyperparameters once set work for a vast variety of natural images.
Yeah, when you perform denoising on images, maybe with fine-grained detail, do you notice a loss of detail or something like that?
So in the images that we have, the architecture itself is very capable of representing discontinuities. And so the detail in the output is relatively good. And that, I mean, even in this like 1D, like even in this 1D case, there can be like adjacent pixels where there's severe jumps to it. So I can't speak to the exact analysis of like the sort of like the zoom in of the detail in this, but it's something that should be expected to be fairly good.
That in practice, people will just pick one initial noise vector and just stay with it? Or do you think that they will stay with it until, because your results is like a high probability result, it'll not work for some particular image, and then people will switch to a different initial noise vector?
Yeah, so this initial noise vector, I mean, I didn't tell you the entirety of the story, right? This initial noise vector doesn't really matter that much, because if you start this network with a sufficiently small size, then the pointwise linear combinations you can get afford you to actually be able to make any item in the basis, or it actually affords you to build an entire basis. And so then basically these C's can compensate for the exact structure of that input vector. But this is just like, these are sort of relatively minor architectural concerns. So the point is, no, it's not going to be tailored toward that exact C. And one thing you could do is also optimize over that input itself, and then that will work as well.
So then if there are no more questions, let's thank the speaker again.